This is a short introduction to torque, and I'm not going to spend a huge amount of time on this. I'm going to hit some highlights. At the very top of the page, where it says background up here, this is the definition for torque, okay, that we'll use. Torque is the ability of a force to rotate an object around an axis. I'm going to just put a little marker on that so you can see that. Okay, so any force applied to a end of a lever arm that causes the lever to rotate about an axis generates torque. Okay, so a lever, one way to think about it, I'll draw a picture over here. It's a wrench. It's a wrench-like device, right? Like you see in these pictures here. And the wrench-like device has some kind of axis, here. Okay, this would be the axis of the thing. It would turn on this axis. Okay, it would turn on this axis right there. And then the torque is applied some distance away from that. And the torque is applied, there's a force applied there. Okay? And so and then that would cause this force applied here would cause the object to rotate like this around the axis. Okay? And that rotational rotation is called torque. Okay, which would be taw. Okay, so let's go into that in more detail. So here's three cases of it. Okay, and so let's talk about whether or not torque is present in each of these cases. So in case A, it has an axis, it has a lever arm, and we apply the torque, and the force is applied here, and that creates a torque. Okay. Okay, torque isn't really a force. It's really a force applied on with a lever arm on an axis. Okay, it's a rotational. It's basically a force applied that makes a some kind of device turn. Okay, so in this case, there would be a torque, and this axis would turn like so. Okay, in this case here, there would also be a torque. There is a difference though, and the difference is the forces here is applied. Here the force is applied at 90-degree angles. Here the force is applied at less than 90-degree angles. And so in this case, if these two forces were the same, the actual torque would be less because the torque is not applied in the most in a way most efficient way because it's applied at an angle. Some of the force is actually down the axis of the lever, and that is inefficient in terms of providing a rotational force. What the part of the force that creates the rotation is the part of it which is applied perpendicular to the lever and causes the lever to rotate. Okay, so the last case is even more extreme, and this is a case where there is no angle and the force is applied down the axis or down towards the axis along the lever arm. And in this case, there is no angle, and none of the force that's applied is applied perpendicular to the lever arm and causes the lever arm to rotate. In this case, if you look at it, ask yourself the question, would this force cause this lever arm to rotate about this axis? And if the answer is no, then there is no torque. So in this case, there would be no torque because this force would not cause this lever arm to rotate about. So the next question it says, is there a directional component to torque? Meaning, does the direction of the force influence the presence of torque? And the answer is yes. Okay, the answer is yes. A force, I'm going to kind of do this in shorthand, a force that's perpendicular to the lever arm would generate the greatest torque. Okay, the greatest torque. Okay, the greatest taw. Okay, taw is the Greek letter for torque. Okay, okay. So if you really want to generate the greatest torque, you want case. So basically, if you want to generate the greatest torque, you want case A. Right here. That's the greatest torque. This would be the next, and then there would be the torque here. This would be the greatest. This would be the middle case, and this would be a torque of 0. Okay, okay. Okay, so is torque a scalar or vector quantity? Well, you can see there's a directionality to it. You can see that you have an axis, you have a lever arm, and you have a force that's being applied, and it's causing this system to turn. Okay, and so rotate about this axis. So since it does, it is a vector quantity. It has a directionality to it. And this, for example, this one would be clockwise. Okay, it would be clockwise. Okay, so it's a vector. Okay, so here's the formula. This thing, I'll write it over here too. This guy right here is tau. That's the Greek letter T, okay, for torque. Okay, and that equals the force, okay, applied, times the length of the lever arm. And the reason it's called R is this is a radius. So this would be R, and this would be the force. Okay, and so this is the radius of the turn. You can see if I turn this, let's say this was a wrench. If I turn this wrench all the way around, I would be turning in a circle. Okay, I'd be turning in a circle. Okay, and the lever arm would be the radius of that circle. So what's the standard unit of force in this class? Well, in this class it's newtons. And what's the standard unit of length? Well, meters. Okay, so what's the standard unit of torque? Well, just multiply them together. You know, force times length, it'd be Newton meters. Okay, so torque is in, torque here is in Newton meters. Okay, okay, there we go. Okay, okay, so let's do one practice problem. These are really simple. Okay, these are not complicated at all. Okay, so first of all, a force. So the formula is tau equals the force times R. Okay, so the force of, if a force of 7 newtons is applied perpendicular to the end of a lever arm, so we could draw a picture of this. We have a lever arm. We have a force of 7 newtons. Here's your force of 7 newtons is applied to a lever arm with a length. So this has an R, that's the R right there, equal to 0.33 meters. What is the magnitude of the torque generated by the magnitude of the torque generated by this force? Notice we're asking for the magnitude here, so there's no direction to this thing. At this point, we're not going to worry about that. So we have 7 times 0.33. And if you multiply those out, you get 2.31 meters. Okay, so take a look at this. I think you know what I've done here, and I think, but this is fairly straightforward. Practice the rest of the problems on the page, and you should be in good shape.